Informally, an infinite sequence A of real numbers is said to converge to a real number L when further and further terms of A get closer and closer to L. The following examples illustrate this phenomenon. Consider the sequence an equals to 1 over n, where n is strictly bigger than 0. Its terms are 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, and so on. As we can see, the terms of this sequence get closer and closer to 0. We say that the sequence converges to 0. On the other hand, the sequence an equals minus 1 to the power n, where n is strictly bigger than 1, whose terms are 1 minus 1, 1 minus 1, 1 minus 1, and so on, does not converge to any number. Neither does the sequence 1, 2, 3, 4, 5, and so on, whose nth term is n. In such cases, we say that the sequence diverges. But how do we give a precise definition of what does it mean for an infinite sequence of numbers to converge to a given number? Thinking of numbers as points of the number line can help to answer this question. Consider the number line and mark a number L on it. If it is so that whatever distance epsilon bigger than 0 we measure from it, left or right, however small that distance is, there will exist a point in the sequence after which all the terms in the sequence will fall in the epsilon region surrounding L. Then the sequence converges to L. This definition can be written out in a single formula using some notation from mathematical logic. Here it is. When a sequence does not converge to any number, we say that it diverges. We say that a sequence diverges to infinity when its terms get larger and larger. More formally, when for any number m, however large, there exists a point in the sequence after which all terms are larger than m. This can be written out using a formula similar to the one above. A sequence can only converge to a single number. Notice that in the definition of convergence, we require that for any non-zero measure epsilon of closeness that we set, the terms of the sequence must all be at least that close to the converging number after some point in the sequence. If a sequence converges to L, then for any other number m different from L, we can set the measure to be the distance between L and m divided by 3. Then, if all terms of the sequence are that close to L, after some point in the sequence, they can no longer be similarly close to m, and so the sequence cannot converge to m. The unique number to which a sequence converges, when such number exists, is called the limit of a sequence. The limit of a sequence A, when it exists, is written as follows. Before we move to examples, let us remark that the limit of a sequence does not depend on the first finite portion of the sequence. That is, if a sequence A0, A1, A2, A3, A4, A5, so on has limit L, then so will the sequence A10, A11, A12, A13, and so on. Indeed, L being the limit of the first sequence means that however close to L, all terms of the sequence will be even closer to L after a certain point in the sequence. Then, clearly, the same will be true also for the second sequence. The limit also does not depend on the domain of the sequence seen as a function. Another sequence, b5, b6, b7, and so on, satisfying a0 equals b5, a1 equals b6, a2 equals b7, and so on, will have the same limit L, also for obvious reasons. Here are two simple examples of a limit. The sequence involved in this formula has all terms equal to 5. It is then obvious that this sequence converges to 5. We have already mentioned this example earlier. On the other hand, the limits minus n to the power n being the sequence, or n being the sequence, do not exist. Both involve diverging sequences, and in the second case we have a sequence diverging to infinity.